Hi everyone! I will show you the first examples of bending moment problems. This is a long problem, so get ready to have some time to work on it. And we will have two main steps. The first step is to find the maximum moment, and second, to find the bending shear, because the bending shear equals the moment time the distance from the centroid divided by the moment of inertia. So the first step is to find that moment. And I will do the long way. I will do the shear and bending diagram so we have all this information. So I will write the steps. I will write the steps at the same time on the left and on the right to make my graph. So number one, what we need to do is find the reaction force. Okay, so we have the free body diagram like this. Okay, we have the force F, that is 10. We have the distance 3. We have the distance 7 meters, and we will have a pin connection. I'm making red my unknown. So this is my AY, my AX, and this is my, let's call that BY, but you can call that also N because it's normal, but let's call that BY. And I will add the letters A and B. So to find the reaction force, you can do sum of the forces on x equals 0, and we have ax equals 0. And we can do sum of the moment about A equals 0. So we get minus 10 times 7 plus by times 10, the total distance, equals 0. And we found by, that should be 7, because we have 10, 10, very easy. Kilonewton. And last one, we do sum of the forces on y equals 0. And we got ay minus 10 plus by equals 0. And we ended up having ay equals 3. So this is the kilonewton. This is the reaction force. And we need them before we can find the shearing force and the bending moment. So number 2, I will do the shearing diagram. And we only have punctual forces, very easy, no really calculation needed. I will do my diagram just below the free body diagram so we can have the forces that fit. We say AY equals 3, now we know, and BY equals 7. So at A, so we will have some changes at A, at 7, and at B. Which color do you want? Let me do a nice color, purple. So at AY, we go up 3 kilonewton. So we will be at 3. No changes, no force, no punctual load, no distributed load, nothing up to the 7 meters. And we drop of 10, so 3 plus 7. So the total there is 10. And it's done because the force is done on the beam. And no force until we get to B. And B, we need to go back up 7. So this is my shear diagram. So anywhere between A and the point that equal to 7, the shear forces will be 3, and anywhere between the point that was at 7 to B, the shear forces will be at 7 and will be negative. So this is my shear diagram. I say shearing. I don't think we say shearing. Let's say shear diagram. We say shearing? Yeah, sometimes we say shearing. And the units are kilonewton, so force in kilonewton. Okay, number 3, the bending diagram. And for this one, we can guess the function, or like at least the visual of the bending moment, what it will look like. So I will show you what it looks like, and we will find the function after. So I keep the same scale for the axe, so we will be there. That will be bending, and that will be kilonewton time meter. Okay, and we will have the point A, the point at 7, and the point B. Okay, was the point at 7. So when the shearing force are positive, the moment increase. And there is no external moments that are applied on this beam, never. So your moment will be continuous, C0. They will never have, you never will have any drop. The drops are due to an external load that is applied to it. There is none. So that will be continuous. So when it's plus, let me use green for this one, the moment will increase. And when the shearing is negative, the moment will decrease. So increase, decrease. We can also see that the bending moment is positive, and that makes sense with the loads, because if we look at this beam, if we push at F, the beam will do this way. And when it's in that directions, that means it's positive. Okay, I will do my little guy. My little guy is positive. Okay, if it bends in that directions, my little guy is sad. It will be negative. Okay, but we are bending in the positive directions. This is one of the slides in the concept and formula questions. So the bending should be positive all the way. There is no way this bending is negative at some point. It will always curve down like a smile. So now the question is, what is the maximum moment there, the moment at 7? Okay. But we will do even more than that. We will find the function m1 of x from A to, okay, I need to give a name to this point. Let's say to C. And we will find the function m2 of x. Okay. For that, we will use the internal forces. I need one more convention there when we will use that. I need the internal convention. So when we cut a beam to find the internal forces, if we cut and look at the left side, or if we cut and look at the right side, the directions of the moment, shearing force and normal force are different. Normal are always pulling outside. Moment are making a little water fountain this way, like going up. And the shearing is down and up. So ups this way. And the convention is for positive, 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 positive. It means if we cut the beam and we look at the left side, we need to use that convention to the left. We need to use this one. This is for the left side. If we cut the right side and we look at the right side, we use that convention. Okay. So we will do that to find the equation. Oops, this is coming. I told you there is a lot of steps. So bending moment, we will start to find the equation from A to C. C is at 7 meters, okay, in our case. So we cut the beam at a distance x that is between 0 and 7, anywhere between 0 and 7. And we add the force that we have on it. What do we have on this one? We have the force A that is pushing there, that is 3 kilonewton. And after that, we draw our unknown forces to the unknown internal forces. So the N, that will be 0, the Vx, and the moment about x, okay? Vx, we already know that will be the 3 kilonewton, that's positive. The N, x will be 0. There is no normal force. And to find the moment about x, we do an equation of equilibrium. So sum of the moments equals 0. Which moment do we have? And I will use the point at x, okay? I will use this point. We will have minus 3 kilonewton time x, the distance, create a negative moment, plus the moment about x, not the moment about x, plus the moment at x, okay, equals 0. So mx equals 3x. So this equation there, m1x equal 3x. So you see it's really easy now to find the moment at point C. The moment at point C will be equal 3 times x equals 7. So 3 times 7 equals 21 kilonewton time meter. Let's find also the moment, the equation of moment to the right. So I have the beam. The distance is always still x, but now the x will be more than 7. So we are cutting between C and B. Okay. So what do we have? We have the F equal 10, that is at 7, and we have the AX equal 3 kilonewton. Okay. And we add our internal forces, Nx, Vx, and Mx. But this one is 2, because this is the second equation. Okay, so it's a bit small, sorry. Let me put it this way. Vx, we know how much it is. That will be at the -7. And x, we know it's 0. What we want to find is mx. And we do another equation of equilibrium. Sum of the moment at the point x, that is there, equals 0. What do you have? We have the force 3 minus 3 times x that create a negative moment about this point. We have the force 10. And that distance there, that will be what? That will be x minus 7. So time x minus 7 and plus the moment 2 of x, the function, equals 0. So we got minus 3x plus 10x minus 70 plus m2x equals 0. So we got m2x equal, so we have minus 3x plus 10x, 7x, and we move it on the other side. So minus 7x and plus the 70. Is it correct, the 70? That looks a lot, but the total is x. Yeah, that looks correct. So my second function there is, oops, in green, minus 7x plus 70. And we can make a check. Do we also find 21 when we are MC? So let's say MC equal minus 7 times 7 plus 70 equal minus 49 plus 70 equal 21 kilonewton. And we really, really want the same value. Remember, it's continuous. We can also check if MB is 0. MB equal the function, so the function is minus 7 times, we are at 10, 10 meter plus 70, this is equal to 0. So the function is correct. And that's super cool. That's super, super cool. So we have made all the steps to draw the shearing and bending moment diagram. Okay, I will do the second steps, but I just want to tell you something. I'm changing this number. That was a bit too small. So that will be, my beam will be 75 millimeter for the base and 150 millimeters for the aids. Okay. So now let's find the maximum bending stress. So step number 2, the bending stress. So the formula is sigma equal m times y divided by the moment of inertia. Okay, what is y? So, oops, let me change this one and this one too. What is y? Oops, 150, 75. Y, that's the distance from the neutral axis, where's the centroid, and the farthest away you are from the centroid, because what's happened with the stress will be distributed like this. Okay, half of them, the beam is bending this way, and half of them are compressed, and half of them are submit tension. And where it's the largest one is on the top and on the bottom. and we want those stress. We want to find the maximum one, because it's always what you want to compare your um, allowable stress with the maximum stress, right? So sigma equal the moment. We will use the maximum moment, and based on our graph, the maximum moment is at point C, and it's 21, and this is kilonewton time meter, so 21,000. That will give us Newton time meter. So I will put everything in Newton, meter, meter fourth, okay? The y, that's this distance, 150 divided by 2, but in meter, so 0.15 divided by 2. And the moment of inertia, the formula for a rectangle is 112 of, so the I is 112 base time h cube, okay? So all those formulas are provided. So we have base, the base is 75 millimeters, so 0.075 time the 8, 0.15 cube. And we get sigma equal, so that gives us 74, 6. Okay, how many 6 do I have? 1, 2, 3, 4, 5, something like this. Okay, do I have enough? I have one more. Pascal, so that gives us sigma equals 74.6 or 0.7 megapascal. And that's the final answer. So let me go over the step again, because we did a lot of steps. Okay, so to find the maximum bending stress in a beam, we need, for the formula, we need to find the maximum bending moment and where it is. Sometimes it's kind of like easy to find, sometimes it's more difficult, so we recommend doing a shear diagram and the moment diagram, because they are linked together. And to find the moment diagram and the shear diagram, sometimes you can do it just by looking at the forces and all of that. Sometimes you need to find the functions, because it's a bit more complicated. And we did the example of a puncture load somewhere in between two normal reaction, and where there is no moment, there's just one puncture load that was applied to it. So I hope that makes sense. Let me know if you have questions for these examples, and we will do some other one just after this one. Bye bye.